Hey, my name is Chen Zhao. It's my pleasure to present our work, Self-Ensembling Gaussian Splatting for Few-Shot Novel View Synthesis.
Let's start by imagining a real scenario. This boy, Jack, visited this tourist place, and he really liked these stone statues. To preserve the memory, he took several photos. After he got home, he looked through these photos to recall the trip. However, he soon realized that the images, captured from fixed viewpoints, were not satisfying. They offered only incomplete observations of the scene, preventing him from fully engaging with it. Compared to the real visit, the experience is far less immersive and realistic.
Fortunately, our Jack is an expert in computer vision. He used 3D Gaussian splatting to generate new images from the photos he had taken. As shown in this video, 3D GS can synthesize realistic images from novel viewpoints. It provides a way more immersive and interactive experience than static photos. This makes 3D GS highly valuable in applications such as cultural heritage preservation, architectural design, education, and entertainment.
To train a 3D GS model, we first need to capture some images as training data. In many real-world scenarios, we don't have access to videos that include images from dense viewpoints. For instance, when Jack visited this place, he only took some photos from the sparse views.
However, 3D GS is very sensitive to the number of training views. As I am showing in this slide, when we train a 3D GS model using 30 views, the novel view synthesis results are pretty good. If we only have 5 training views, the results become much worse. We can see many artifacts in the synthesized images.
Here we have a more detailed analysis. We trained 3D GS models with 3, 6, and 9 views. The left figure shows the PSNR of images rendered from training views across different training iterations, and the right one reports the PSNR of test views. We can see the performance on test data drops while the training results steadily increase during training. This means the model suffers from an overfitting issue.
Besides, the performance gap becomes larger when fewer training views are used, meaning that the overfitting is more severe as fewer images are available. To handle the overfitting issue, a straightforward baseline is ensemble learning. This shows a general pipeline of ensemble learning. During training, we train several models separately. At test time, all models are applied to the input, producing multiple predictions. A voting module then aggregates these predictions into the final output. This ensemble learning strategy can reduce the bias of each individual model and thereby enhance robustness. However, it needs to train multiple models and run all trained models during testing, which is computationally expensive.
To improve efficiency, one could utilize self-ensembling. In this framework, only a single model is trained, and the variants are dynamically created throughout training. During inference, only a single forward pass is needed. This makes both training and testing more efficient. The information from the variants is aggregated during training, achieving robust ensemble learning.
Motivated by the benefits of self-ensembling, we aim to enhance the robustness of 3D GS in the sparse view setting through a self-ensembling approach. However, it is non-trivial to achieve effective self-ensembling for 3D GS. A straightforward approach is to create variants by adding random noise to all Gaussian primitives. Unfortunately, this makes the variants too diverse and leads to a significant drop in performance. Here I am showing an example. For this novel view, an optimized 3D GS model generates a clear image. However, once we slightly perturb the Gaussian primitives with random noise, the RGB rendering becomes super noisy.
To handle this problem, in this work, we introduce an uncertainty-aware perturbation strategy. We train a 3D GS model using the available training images. Besides, we sample some pseudo-views and render an image from each pseudo-view using this model. The renderings at different training steps are stored in an image buffer. For each image buffer, we compute the pixel-level standard deviation across the images in the buffer. We then introduce a local smoothing process by averaging the uncertainty scores within a sliding window to improve the robustness, which generates the uncertainty map for this image buffer. We mark the pixels with high uncertainty scores as uncertain ones, since their RGB values fluctuate significantly across training steps.
We dynamically update the image buffers and the corresponding uncertainty maps throughout training. During each update, we add the latest pseudo-view rendering to the buffer and remove the oldest one. We label the Gaussians corresponding to the pixels with high uncertainty scores as uncertain Gaussians, and we add random noise only to these uncertain Gaussian primitives. This creates a perturbed variant from the original model. By default, we sampled 24 pseudo-views, which leads to 24 uncertainty maps each time.
Here I am showing the update of uncertainty maps across different training steps. Our method introduces dynamic uncertainties, thereby creating diverse variants. This ensures the effectiveness of the following ensemble learning. These are the images rendered from pseudo-views using the 3D-GS model and its perturbed variant during training. The images rendered using the variant are still clear. They don't get too noisy after perturbations. This means our uncertainty-aware perturbations lead to reliable variants with reasonable noise.
Now we have the variance based on uncertainties. The next step is to do self-ensembling. Here, we name the model we perturb as delta model. After the perturbations, we get a variant from the delta model. Additionally, we introduce another model called sigma model. We render the images from some pseudo-views using the variant and the sigma model. An RGB loss is computed between these two groups of renderings as the supervision. We also supervise the training of the delta model and the sigma model using the available training images. Once the training is done, the sigma model is actually an ensemble of the all variants created during training, which aggregates the information from these variants. We only keep the sigma model for inference.
In our pipeline, we supervise the training of the sigma model using RGB loss with ground truth training views, and we add a regularization term to achieve self-ensembling. Compared with the baseline, first, we only perturb uncertain Gaussian primitives for the delta model. Second, we don't have any perturbation for the sigma model. These make our method much more stable.
Next, I am going to show a detailed analysis of our uncertainty-aware perturbation strategy. Here, I compare our method with the baseline, CORGS. As we can see from these two figures, if we enhance the ensemble learning by training more Gaussian models in CORGS, the PSNR does increase. However, the training speed significantly drops, which shows the limitation of ensembling learning in terms of efficiency. Besides, the PSNR stops increasing after we use 5 models in CORGS. I will be explaining this in the next experiment.
In this figure, the x-axis measures the similarity of all involved variants, and the y-axis is the PSNR result on test data. If we discard the uncertainties and simply perturb all Gaussians, the resulting variants become too diverse with low model agreement score. The ensemble learning is then unreliable, making the PSNR much worse. Moreover, if we use 8 models instead of 5 in CoreGS, the similarity among variants doesn't change that much. This means the additional variants don't introduce sufficient diversity for more effective ensemble learning, and this is why the performance does not increase.
These are some quantitative results on LLFF and DTU datasets. More results are reported in the main paper. Here, we evaluate the methods with 3, 6, and 9 training views. Compared with the original 3D-GS, our method achieves much better results. Additionally, we evaluate pre-trained MVS Splat, which is a generalizable feed-forward method. In the sparse view setting, there is still a huge performance gap between the optimization-based method and the feed-forward method, meaning that the optimization-based method is still quite valuable for realistic novel view synthesis.
Here are some qualitative results in the sparse view setting. Compared with 3D-GS, our method gets much more realistic images for novel views with fewer artifacts.
Thank you very much, and see you at ICCV Oral 2A and Poster Session 2.